Hello. Hello, everyone. Can you hear me all right? Brilliant. Okay. Great to see you all. I'm finally back. Just waiting for a few more people today to join. So today we're going to talk about electrostatics and, of course, about the Gauss law a little bit. Gauss law is not part of the school program, but we decided to challenge you a bit and to actually give you some interesting stuff. Because I mean, you'll study capacitors in year 13 if you haven't already, and it's a reasonably straightforward topic with some differential equations where you need to charge and discharge the capacitor. But overall, the exciting physics happens in the Gauss law mostly. Okay, so I've prepared 7 questions for you today. Share my screen. And we'll start with an easy one. Okay. Share. Okay, so the first question is very straightforward, actually. It's just the use of Coulomb's law. It says, find the electrostatic force between two charges, 1 coulomb and 2 coulombs, which are 1 kilometer apart. So you can sort of understand what sort of what we're dealing with. And we're dealing with two charges. Does it matter if they're positive or negative? Can someone tell me? So 1 coulomb and 2 coulombs. Does it matter? Well, it's if you're looking for the magnitude of the force, it doesn't really matter. Of course, the force would be attractive if they're oppositely charged. If they're positively charged, it would be a repulsive force. But the magnitude of the force will be the same. So it doesn't really matter. If we're looking for the force, and in physics, when they say find this force, by default, it means the magnitude of the force. You would say magnitude and direction if you were looking for a vector. So they're 1 kilometer apart, so that's 1,000 meters. 1,000 meters. And we know that the force can be found using the Coulomb's law. It's 1 over 4 pi epsilon 0 or epsilon naught multiplied by Q1, Q2 divided by R squared, where R is the distance between them. And you know that this term is also known as K, the Coulomb's constant, K. But in physics, we tend to use 1 over 4 pi epsilon 0 squared. Right. So 1 over 4 pi multiplied by epsilon 0. Sorry, I sometimes forget the value. Epsilon 0. It's 885 times 885 times 10 to the minus 12 to the minus 12 multiplied by Q1, which is 1 coulomb, multiplied by 2 coulombs, divided by the distance between them. That's 1,000 meters squared. And it seems like a boring question right until the point you get to the answer. So 1 over 4 pi multiplied by epsilon 0 multiplied by 2 over 1,000 squared. And you get a value which is 18,000 newtons. And that's the surprising thing about this. It's like, how can that be? It's two charges 1 kilometer apart. It's a very big distance, and two charge. Well, a coulomb of charge, well, it doesn't really have size, but it could easily fit in a golf ball. Yeah, it can easily fit. You can easily fit 1 coulomb of charge in a golf ball on a golf ball, and 2 coulombs also. So basically, two charged golf balls a kilometer apart, and the force is immense. What's 18,000 newtons? What, that's 1,800 kilograms of force. We used to measure force in kilograms. Basically, it's such a force that can lift 1,800 kilograms. So it's a very large force. And the thing is, why this is surprising is because the coulomb is actually a massive quantity. 1 coulomb of charge is a lot. Is a lot of charge. And when you consider current, for example, 1 ampere, 1 ampere means 1 coulomb per second. 1 coulomb per second. That means 1 coulomb of charge, 1 whole coulomb of charge flows in 1 second. So 1 ampere is a lot of current. And yeah, so that's quite an interesting one. So yeah, not a mistake. It's just it is. There are also questions like, what? Let's say you have a kilogram of steel and another kilogram of steel, and if you were to remove all the electrons, yeah, so just take away all the electrons. That's what 26 electrons per atom. If you were to remove them and place them, I don't know, 10 kilometers apart, what would the force between them be? And if you do the calculation, you do it as a home exercise. So 1 kilogram pieces of iron, you remove all the electrons, and the force between them will be absolutely massive. It's because the electrostatic force is a very, very strong force. The coulomb. Well, the coulomb was initially derived from current, from ampere, and ampere was derived from the magnetic force between them. And magnetic force is not that strong. So if you take two wires and run a current of 1 amp through them, the force at some fixed distance would be, the force between them would be 1 Newton. So 1 ampere, it links the ampere, the Newton, and the coulomb all together. So that's why coulomb is convenient, even though it's a massive quantity. And the same for farads. For the capacitance of a capacitor, the farad is a massive quantity, and we normally measure capacitance in microfarads, nanofarads, or even picofarads. So the motivation is the SI system of measurement, which links all the units together. And sometimes they have situations like that. Okay, let's move on to problem 2. Find the equilibrium position of a positively charged ball inside a hollow tube with positive charges Q1 and Q2 fixed at its ends. Is it stable equilibrium? Okay, so we have a positive charge here, Q2. We have a positive charge here, Q1. And we have a ball, which is also positively charged, and the charge is Q. Right. So we can say that the ball Q experiences two forces. One to the right, let's call this force F1, and one to the left, let's call this force F2. And of course, if it's in equilibrium, these forces have to be equal. So let's take this distance to be x, and this distance to be L minus x, obviously, because the length L minus x, and find the two forces. So F1 is going to be 1 over 4 pi epsilon 0 multiplied by Q, Q1 divided by the distance squared, x squared. And F2, the second force. Well, I'm doing modulus of forces. I'm not really interested in the direction because the direction is obvious from the diagram. Mostly in physics, you do that. If the direction is obvious, you don't bother with the signs. So I'm just making them all positive. 4 pi epsilon naught times Q multiplied by Q2 over L minus x squared. L minus x squared. And of course, the forces are equal. Therefore, we can say that 1 over 4 pi epsilon naught Q1 over x squared equals 1 over 4 pi epsilon naught Q2 over L minus x squared. So we cancel these, we cancel Q, and we're left with, we need to find x eventually. So it doesn't look like we can easily cancel it out or anything. So we'll just crisscross. So it's cross multiplication, Q1. Actually, there is something we could do. So I'm going to do it slightly differently. So I'm going to say L minus x squared. So I'm trying to avoid unnecessary opening of brackets until I'm absolutely certain I can arrive at a reasonably easy answer. Q2 over Q1. And here I'm going to make it into one fraction. So it's L over x minus 1 squared, which doesn't really look good, but yeah, what are you going to do about it? So Q2 over Q1. Take the square root of both sides. And of course, L over x is greater than 1. So this is a positive value. So you can't have x, which is greater than L. This is going to be a positive value. So we only consider the positive answer. So Q2 on Q1, add 1. So L over x is 1 plus square root of Q2 on Q1. And find x. So from here, x is it's going to be L square root of Q1 over square root Q1 plus Q2. Yeah, I skipped a step, but hopefully you understand how I got here. Yep. Does does are you okay with the maths? I mean, it's not rocket science. The maths is not too hard. Does everyone understand the maths part of this? Type something. If you don't, do ask me a question. Okay. Yeah. So it should be reasonably easy. The interesting question is, so we found the equilibrium position. We can check that it is in fact less than L, and that makes perfect sense because obviously Q1 plus Q2 is greater than Q1. So this is a fraction. So this is a fraction which is less than 1. So it is a fraction of L, and it's going to be less than L. This is going to be less than L. So that makes perfect sense. This is how I check my answers if I want to. Like, does the answer make sense? It does. Now the question is this stable equilibrium? So what do you think about this? Would that be a stable equilibrium or unstable? Please type the word stable or unstable in the chat. What do you think? All right. So we have different views. So, Josh, would you like to elaborate? Why do you think it would be stable? And Adam, would you like to say why it is unstable? That's a good point. What about you, Adam? What is stable equilibrium anyway? It would be SHM. Well, probably not SHM. Because for SHM you need a linear relationship. Basically, that means that for SHM you need that the force is proportional to displacement, and as we see, the force is proportional to displacement squared, to inverse of the displacement squared. So probably not SHM. But what is stable equilibrium? Can you tell me? Can you tell me what is stable equilibrium? And if it were no resultant force. Okay, not quite, Josh. No resultant force means equilibrium. So let's look at a situation. Let's say you are on the top of a hill, and if you're at the exact top, you have an upwards force, normal force, and the downwards force, which is weight. Ah, yes, Adam. If it's displaced, it will return to equilibrium position. Exactly. That is what stable equilibrium means. So, Josh, if in this case the resultant force is 0, but this is unstable equilibrium. Unstable. The thing is that if you displace the ball, slight gently to the left, it will not return to its original position. Whereas in stable equilibrium, stable, if you were to, so here the picture is the same. So normal reaction and weight are the same two forces. But if you were to displace the ball to the left, it will return to original position. So this is what we call stable equilibrium. This is unstable. So here, if we were to shift the ball So let's say the ball is here now. Now the F2 force would decrease. The F2 force would decrease and F1 would increase. So you would have a force that is trying to return it to the equilibrium position. And if you were to displace it to the right of the equilibrium, the opposite would happen. You would have a bigger force to the left trying to return it because it's getting closer to Q2, and a smaller force to the right, which is pushing it away. So if you push it sideways, it will return to equilibrium. What about if the ball was negative? Well, if the ball was negative and it was in equilibrium, you have a force from the left, which is F1, and a force to the right, which is F2. F1 is pulling, not pushing this time. So it's pulling to the left, and F2 is pulling to the right. And if you were to displace the ball to the left, the F1 force would increase because it's getting closer to Q1, F1, and the F2 force would decrease, F2. So therefore, it will keep moving to the left. So it would be in unstable equilibrium. So, and also you could use the logic of potentials. You would see that at this point it has minimum potential, and it would stay in this position. But if it was negative, it would move in the it would move in a way so to reduce the potential. Anyways, okay. So I hope that makes sense. Okay, problem 3. And you've seen this problem. This almost exact same problem you have in the assignment. I think it's question 4 or something. 3 charges, 2 microcoulombs, minus 4 microcoulombs, and 6 microcoulombs are placed in corners ABC of a square ABCD. Find the electric field at D. Field at D if the side of the square is 1 meter. Okay, so as usual, we draw it first. So we have A, B, C, D. A, B, C, and D. And there's a positive charge here, plus 2 microcoulombs. At B, we have minus 4 microcoulombs. And here we have 6 microcoulombs. Okay, coulombs. Right, and we have three electric fields, 3 separate electric fields. So EA would be a downwards electric field. Let's call it EA. Now there won't be a leftwards electric field, slightly bigger. Well, actually exactly 3 times bigger because the distance is the same. So that's EC. And another electric field, which is going to be towards B. Let's call it EB. Okay. Well, we can find them separately, and that's reasonably easy. So EA, we know that the electric field. So there's a question for you. Do you understand how electric field is linked to electric force, to electrostatic force, to the Coulomb's force? Do you understand the link between the field and the force? Yes or no? field causes the force, yes, but there's an equation. There's an equation that links them. Yes, F over Q, exactly. The equation is F over Q, so we know that E is F over Q. So let's say for charge A, if we place a small charge Q, let's say Q naught, the electric field from A is going to be the force from A divided by Q naught. And the force from A is 1 over 4 pi epsilon naught Q A Q naught divided by R squared, and all over Q naught. All over Q naught. So Q naught cancels, and we're left with 1 over 4 pi epsilon naught Q A divided by R squared. So basically what I'm saying is the electric field has almost the same equation, except it's just Q. So we know the electric force is 1 over 4 pi epsilon naught Q1 Q2 over R squared. That's the force. But the field is the same equation, but with just one Q. Naught Q over R squared, where Q is the charge that is creating the field. They're just creating the field. And here it's one charge is sort of creating the field and the other charge is inside that field. So, okay, back to EA. So using that formula, EA is 1 over 4 pi epsilon naught QA divided by radius, which is 1. And of course, you can find the value because it's all numerical. It's all numerical, so it's going to be 1 over 4 pi multiplied by epsilon naught multiplied by fraction. QA is 2 times 10 to the minus 6 over 1. Wow, well, it's quite a big value. So it's 17.9 kilonewtons. Oh, what am I saying? It's not newtons, of course. 17 point. Okay, let's put it 70. Well, it's 18,000. 18,000 volts per meter or newtons per coulomb. So newtons per coulomb. EB, the electric field from B, is a very similar expression, 4 pi epsilon naught QB divided by, now the distance, if this is 1 meter, this is going to be square root of 2 meters. So divided by square root of 2 squared, so divided by 2. And so it's going to be 4 divided by 2. So it's actually going to be the same thing because it's QB is also 4, but divided by 2, it will become 2. So it's 18,000 newtons. 18,000 newtons per coulomb. And finally, EC, it's 1 over 4 pi epsilon naught QC divided by 1 meter again. And if you remember, because everything is constant except the charge, and the charge is 3 times greater than A, so it's just going to be 3 times bigger than that. So 18 times 3, 54,000. 54,000 newtons per coulomb. Now, the meaning of the 54,000, that means that if you place a 1 coulomb charge inside that field, I mean, 54,000 sounds like a strong field. If you place a 1 coulomb charge in that field, it will experience 54,000 newtons of force. But as you remember, 1 coulomb is an incredibly large charge. So it's not really such a big, field, such a large field. It's a very typical field created by 3 very, very small charges. And then all you need to do is just to be able to add vectors. So different ways to do this. You can use well, I'd find the vertical. I'd find the vertical EX and EY separately. So EX is going to be in this direction. So it's going to be EB cos 45 minus EC. So that's going to be 18,000 cos 45 minus 54,000. So it's going to be minus 41,300 newtons per coulomb. This is approximately, of course. And EY is going to be EB sine 45 minus EA. That's the vertical component of the field at B. Sorry, at D, of course, the field. And that's going to be minus 18,000. So it's going to be minus 5,300 newtons per coulomb. Right, so we can see that the field is left and down. So the field at this point is left and down, and it's stronger in that direction. So roughly we have a field like this. We call this ED. So ED is square root of 5,300 squared plus 41,300 squared. I'm doing it slightly unconventional, doing y first, but it doesn't really matter. So square root of 5,300 squared plus 41,300 squared. That's 41,600. So 41,600 newtons per coulomb. And to find the angle, let's say we want this angle, theta, the direction. We need the opposite over adjacent. So opposite is EY. So it's inverse tan of 5,300 over 41,300. Now, notice how I'm ignoring the signs. I'm just completely ignoring them because I have a diagram, and it is very obvious from the diagram. The direction is very obvious from the diagram. The fact that they are negative, I've already used when drawing the diagram. So I'm not using the negative values, because once you start inserting negative values into your arctan, it becomes a mess, like literally a mess. So if you can, always stick to angles below 90 degrees and always try to avoid negative values when you can. Of course, you need to be careful with this, but as you can see here, it's just, yeah, I'm just using the positive values, and it gives me some value, which is not particularly interesting. I'll just do it for the sake of it, 41,300. And it gives me 7 degrees, 7.3 degrees. 0.3 degrees. So yeah, the angle is 7.3 degrees. You can say it's 7.3 degrees south of west, south of west, and yeah, that's it. Or just 7.3 degrees to the horizontal, of course. All right, now coming to actual interesting stuff. Find the electric field at point X. Sorry. So here we used the principle of superposition. The principle of superposition says that superposition is that the total electric field is equal to the sum of individual electric fields. It's the vector sum. E2. And I've demonstrated it. So I was just adding vectors plus etc. Or simply you can say it's the sum of e's I from 1 to n. If you have n electric fields, the total electric field is the vector sum of all of them. Right. You have a charged string. So when we say string, we usually mean it's quite thin. It's charged and with a charge density per unit length rho. So what does it mean? Well, it means that rho is charge per unit length. So per unit, charge per length, literally, or charge per unit length. Usually we can say delta Q, delta L, although not necessary. Just charge per unit length. That's the definition of the density per unit length, or charge per unit length. Right. Anyways, you have a charged string. Now, the question does not specify whether it's positively or negatively charged, but the only difference that makes is the direction of the field. And once again, they're not asking us for the direction of the field because there's an obvious answer. If it's positive, the field is going to be to the right. And if it's negative, the field is going to be to the left. So that already throws away some of the thinking. You don't have to think about the direction. So just find the magnitude. So it's a positively charged string, and you need the field. So any thoughts? Any thoughts? What we could do? And it involves the superposition principle, of course. The string is uniformly charged. Yes, Adam, can you just elaborate a little on this? What do you mean by sum of the fields from the string? Isn't it just one field? Oh, Josh, yes. Very nice. We do need to integrate, but what do we need to integrate? Rho with respect to x. Or displacement. Okay, well, rho will be involved. Displacement, yeah. Um, in general, when you say integrate, what do you mean by integrate? So, and how is that linked to Adam's words? Sum of the fields from the string. Can you combine these two together, because that's actually what we need to do. Integrate the fields. Well, yeah, exactly. Sum all of them. You need to cut the string into small chips, into small bits. And let's call this bit 1. And this bit is charged. We can say it's positively charged. And it creates a field, E1. E1. This bit, the second bit, is also charged. And it creates another field, E2. And effectively, we need to find this total charge from all of these bits. Oh. Okay. So let's say we define a distance. We define a distance lambda. Lambda is the distance. And we take a chip of, at that distance, we take a very small chip of width d lambda. D lambda. And, oh, actually, you know what? Let's call it delta lambda, just for the sake of it. Delta lambda. That's the width of that piece. Now, as I said, the charge density is charge over length. So from here, the charge of that bit, delta Q, is going to be rho times length. So it's going to be rho times delta lambda. That's the charge of that little piece, charge Q. And the field that it creates, let's call it delta E. The field that it creates is going to be 1 over 4 pi epsilon naught multiplied by Q, delta Q, divided by the distance. And the distance is lambda plus x squared, because that's the distance to that point. Brilliant. Brilliant. That's the charge. So what we need is we need the sum of all delta x, delta e's. So the total charge is sum of all delta e's, which when you take the limit is the integral of delta of d delta, not delta, de. Okay, so I won't do that. Just a second. I just want one more step. Sum of delta e's. So sum of all of these. And what I'll do, I'll start numerating them from the left. 1, 2, 3, 4. It doesn't really matter how I do it, just for convenience. So here's the distance is so we need lambda. So this is 0 and this is L. So lambda changes from 0 to L. Okay, so it's going to be the sum of this thing, 1 over 4 pi epsilon naught delta Q. And delta Q is rho delta lambda. So it's going to be rho delta lambda divided by lambda plus x squared. Lambda plus x squared. And we know that if we tend delta lambda to 0 as delta lambda tends to 0, this becomes E. So E is approximately equal to that. E becomes exactly equal to the integral of 1 over 4 pi epsilon naught rho. Now it's not going to be delta lambda now, it's going to be d lambda, because as delta lambda tends to 0, delta lambda becomes d lambda over lambda plus x squared. Ooh, exciting. And of course, we know that lambda, because the lambda is the variable, and lambda changes from 0 to lambda, to L, sorry, 0 to L. So we start from the right where lambda is 0, and we move all the way to the left where lambda is L. Therefore, I can write, so 1 over 4 pi epsilon naught is a constant, so I can take it out. Rho is a constant, so I can take it out. So it's going to be rho 4 pi epsilon naught integral from 0 to L. Now, this is not a logarithm. This is not going to be a logarithm. So it's going to be a x to the power n bit. So I'm going to write it like this: lambda plus x to the power minus 2 d lambda. So once again, rho 4 pi epsilon naught. Right, so we need to integrate that. So it's going to be lambda plus x to the power minus 1, lambda plus x to the power minus 1 over minus 1. So just a simple integral from between limits 0 and L. So substituting L into this and taking out the minus, it's going to be minus rho 4 pi epsilon naught. So substituting L, so it's going to be 1 over L plus x minus 1 over x. And you find the common denominator here. It's going to be x minus L minus x. So x cancels out. It's going to be minus rho L, and you have minus here. So it's going to be rho L divided by 4 pi epsilon naught. And then here you will have x multiplied by L plus x. And that's it. That's the relationship. So if you know x, you can find if you know x and you know L, you can find the electric field. Did I lose anyone? So how well do you understand? On a scale of 0 to 10, please let me know. Very nice. Very nice. No problems with the integration, I hope. It's a sort of an unusual integration where we do integrate with respect to lambda, not with respect to x. Edward, how are you? Haven't heard Much from you? Okay, also 10. Very nice. Brilliant. So okay, moving on. We are approaching the Gauss's law. So this, like problem 4, is roughly A-level physics, maybe a tad higher. Now, Gauss's law is not in the A-level program, but hopefully you'll find this interesting. The electric flux. Have you studied magnetic flux? Guys, have you studied magnetic flux? No. Okay. Well, you will study magnetic flux in year 13. Basically, what is magnetic flux? You have a magnetic field. So let's say you have a bar magnet, and you have all these magnetic lines going out. And we know that the magnetic field is B. You should know this from GCSEs. B is the magnetic field. It's actually called magnetic flux density. You've probably heard this. B is magnetic flux density. So what does it really mean, magnetic flux density? Well, you know that the closer the magnetic field lines are, the stronger the field. Magnetic flux is how much of that field, like how many lines. So if you take a loop, so for example, if you take a loop here, loop of area A, the magnetic flux is actually how many magnetic lines pass through that loop. And flux can be found like this. Flux is the magnetic field multiplied by area. And there's of course cos alpha, because if the loop is sideways to the magnetic field, nothing will pass through the loop. So that's why we have cos alpha, where alpha is the angle between the magnetic field and the normal to that. So this is the normal to that loop, the normal vector to the loop of wire. And we're interested how much of the magnetic field actually passes through that loop. So how many magnetic lines can we catch with that loop? And this is what flux is. The more lines we capture, the more flux. Okay. So you can increase flux by increasing the area, or you can increase flux by increasing the strength of the field. Is that making sense? My explanation on a scale. Yeah, let's make it on a scale of 0 to 10. Okay. Magnetic flux is measured in Webers, and if you have a magnetic field, let's say 0.2 Tesla, and the area of the loop is I don't know, 0.5 square meters squared, the flux, and it's at right angles. If the loop is at right angles, if theta is 90, if theta is 90 degrees, oh, sorry, not 90 degrees, of course, 0 degrees. 0 degrees. 0 degrees, that means the loop is exactly perpendicular to the field. So you have the field and its loop, because we are not looking at the loop itself and looking at the normal to the loop, which is like this. So the normal is parallel to the field. So the angle is 0 degrees. So the flux is going to be B times A, so 0.2 multiplied by 0.5. This is year 13 stuff. This is what you will study in the hopefully beginning of year 13. 0.2 times 0.5 times cosine 0, so 1. So that's going to be 0.1 Webers. Okay, so magnetic flux is measured in Webers. And yeah, and if theta is 90 degrees, that means the field, the loop is along the field. So no magnetic fields can, no magnetic lines can actually pass through the hoop, pass through the loop of wire, and therefore the flux is going to be 0.2 times 0.5 times cosine of 90, which is 0, so it's 0 Webers. So this is the idea behind the magnetic flux. The idea of the electric flux is exactly the same. It's how much electric field can we capture with a surface. So we have a surface, not necessarily a loop. It's a surface of wire, and how much of the electric field can we capture? And the flux, the electric flux. So this is the magnetic flux. This is the magnetic flux, and the electric flux is just EA cos alpha. Cos alpha. So nothing. It's pretty much the same thing. And it says, what is the electric flux through the curved surface of the truncated cone? Basically, if you imagine the electric field like water, yeah, which is sipping through. So imagine, I don't know, rain. I like to imagine rain. So it's raining and the rain goes in this direction. Not a typical direction for rain, but can happen, especially in mountains. It can rain upwards. Can rain upwards. So the rain is going this direction, and this is an imaginary cone. The question is how much of that rain passes through the curved surface. Okay. And the Gauss's law says that if you have a surface, some kind of surface, it doesn't really matter what surface it is, and you have some charge inside it, so you have a charge inside it. It says that the total electric flux through that surface, Gauss's law says that the total magnetic flux through any surface is equal to the charge inside that surface divided by moment of embarrassment, divided by epsilon naught, of course, epsilon 0, where epsilon 0 is a constant. So basically the electric flux is proportional to the charge inside that sphere. In this case, there's no charge inside that sphere, inside that surface. There's no charge inside. All the field is outside. So what does that tell us? That the total flux through all the surfaces is is zero, exactly. Because there's no charge inside, the total flux is zero. And we need to find the flux through the small surfaces, or through the flat surfaces, and we need to find the flux through the curved surfaces. Basically, that means that the flux, let's call it flux 1, flux 2 for the big circle. So flux through this, okay, I'll actually write it, small circle, plus the flux through the big circle, plus the flux through the curved surface is going to be equal to 0. The total flux is 0. And the flux through this small, so we introduce an area vector. An area vector is a vector that has the same magnitude as the area. So area vector. It has the same magnitude as area. And the direction is the same direction as the normal to that surface. And if it's a closed surface, the we say the vector is, if the vector is outwards. So for this surface, the area vector has this direction. It's perpendicular to the surface, the area vector, and its magnitude is equal to that. And E is in this direction, and this is the angle between them. So the flux through the through the big circle is going to be E multiplied by the area, and the area is pi r squared multiplied by cosine alpha, because that's the angle between the two vectors, the E vector and the area vector. Brilliant. Now, the flux through the small circle, Now, the area vector is going to be in this direction. A2, A1, and A2. So we can say, because it's always outwards, it's always out, it's an outside vector. The normal vector is the outside vector, and therefore we can, well, there are different ways we can do this. We can say the angle between them is pi minus alpha. Yeah, because if this is alpha, this is pi minus alpha. So it's going to be E pi r squared cosine pi minus alpha. And if you studied your trigonometry well, you know that cosine pi minus alpha is minus cos alpha. So it's going to be minus E pi r squared cos alpha. Or you can simply realize that, well, the flux is in the other direction. I mean, in this case, the flux is going outside of the cone, and here the flux is going into the cone. Therefore, you can work out that one of them is positive, one of them is negative. And finding the flux through the curved surface is going to be a massive undertaking. It's possible to do it through very complex integration. But we have this. And actually, Um, we actually we've done everything. So we know the flux through the small surface is minus E pi r squared cos alpha plus E pi r squared cos alpha plus phi curved, the thing that we're looking for, is equal to 0. That's all we need to find the flux through the curved surface. Because we know we can calculate the flux through the small circle, we can calculate the flux through the big circle, and we know that the total flux is 0. Therefore, we can work out the flux through the curved surface. So it's quite an ingenious way of avoiding horrendous integration, which would be absolutely horrendous. You need to split the curved surface into infinitely many small pieces and find the flux for each surface. But no, here you don't. So the answer is E pi cos alpha. This is a common factor, and it's going to be r squared minus r squared. So the flux is going to be negative. That means more flux is coming in than coming out. But it doesn't really matter because we're looking for the flux. We're looking for the magnitude of the flux. So the magnitude of the flux, because this is definitely going to be a negative value because r squared is smaller, but the magnitude of the flux is E pi r cos alpha r squared minus r squared. And that's the answer. Right. So, do you understand this solution, and do you understand this question overall? Do you understand what flux is? Please comment in the chat. Is there something you don't understand about this question or about flux in general? I'm happy to comment. So if you imagine electric field, that an electric field is like rain, then flux is how much water you can capture with a surface. It doesn't really matter what kind of surface it is. Like for example, if you were catching rain, the only thing that would matter is the cross-sectional area. If you have a bucket, you need the cross-sectional area of the bucket. So please do comment. Okay, on a scale of 0 to 10, how well do you understand this problem? I'd like answers from everyone, please. Why was the total flux through the cone is 0? This is Gauss's law. Gauss's law that the total flux through any surface, it doesn't matter what kind of surface it is equal to the charge inside that surface divided by epsilon 0. And the charge inside that surface is obviously 0. It's not a charged surface, it's just a cone inside an electric field. Therefore, the total flux is 0. Does that make sense, Adam? Okay. So Gauss's law is a very powerful tool, and you can use it to find the field next to a infinitely charged plate, for example. How much time do we have? I mean, the question, there's an amazing video. So if you look at question example 7 in the assignment, there's a link to an absolutely amazing video of how to find the electric field next to a infinitely charged plate. So if you have an infinitely charged plate with charge density sigma, that means charge per unit area sigma, then next to that plate, the electric field is going to be sigma divided by 2 epsilon 0. And we use that fact to determine the um, to determine the electric field. To determine the electric field in a capacitor, for example, because a capacitor is two charged plates. Okay. Oh, actually, we do need this fact. We do need this fact, and the electric field. So, okay. Let's say you believe everything I say, and when I say that electric field next to an infinitely charged plate is sigma divided by 2 epsilon 0. We do need to explain what sigma is. So I'm going to take this and put it over here. Right. So we have a charged. We have a charged plate. So what does it mean? It's an infinite plane which is charged. And you will see that the electric field, because it's symmetrical in all directions and it's infinite in all directions, you will see that the electric field is away from the plate. So the electric field goes parallel to the plate. Well, parallel to the area vector of the, okay, parallel to the normal. Anyways, the electric field is like this. And no matter how far you are from that plate, the electric field is going to be sigma divided by 2 epsilon 0, which is quite peculiar, meaning that if you go further away from the plate, the electric field will still be the same. Yeah, it doesn't depend on the distance from that plate. And let's say you believe that this is true. Sigma, as I said, is the charge per unit area. Charge per unit area. And we'll need that fact. Now, the next question is very simple, similar to problem 13. An infinitely charged slab of thickness h and volume charge density rho is placed horizontally. Find the electric field as a function of z. So they're not saying whether it's positively or negatively charged, but we assume it's positively charged because it doesn't really matter. It doesn't really matter which one it is. It's just going to be symmetrical answer for a negative charge. So when we say charge density rho, we mean that it's charge per volume. It's the charge per volume. Charge per volume. So you can't really find the total charge because it's infinite. It's infinite in both directions. But what you can do is realize that this is a slab made of many infinite surfaces. Many infinite surfaces. Etc. And if a surface, let's say a surface has thickness delta H delta H is the thickness of a surface of a thinner slab, then the volume of that thinner slab, well, no, doesn't make any sense. Well, yeah, the volume is area multiplied by delta H. And we know that rho, as we have already mentioned, is Q divided by V. Q divided by, all right, V is usually volume. So it's Q divided by A delta H. A delta H. And if we multiply by delta H, we get rho delta H is equal to Q over A, which is also known as sigma. So sigma for this plate is the charge volume density times delta H. This is an important result. So I'm just playing with equations here just to find sigma. And we know that the electric field from a single slab is going to be sigma divided by 2 epsilon 0, 2 epsilon naught. So let's say I am right here. I'm at this point above H, and all the plates are below me. So the total electric field is going to be just the sum of all the fields. So let's call it E A at this point. EA is going to be E1 plus E2 plus etc. plus En. Let's say we have n slabs, which is actually so E1 is going to be sigma divided by well, it's not sigma, it's rho delta H. It's rho delta H1, the thickness of the first slab. Yeah, it's called 1, 2, 3, 4, 5. Divided by 2 epsilon naught plus rho delta H2 of the thickness of the second slab, 2 epsilon naught plus etc. plus rho delta H n 2 epsilon naught. So as a matter of fact, we can take rho over 2 epsilon naught out, and we have delta H1 plus delta H2 plus delta H3 plus etc. plus delta Hn. So what do I get if I add these all together? Delta H1 plus delta H2 plus delta H3. What do I get? H, of course. Of course I get H. So it's going to be rho H 2 epsilon naught. I kind of got the general result, because if I have a slab of thickness H, the electric field is going to be rho H over 2 epsilon naught. This is a very similar result to the sigma over 2 epsilon naught. So I kind of went from the electric field from a slab of thickness H is that. And so if I generalize this result, and let's say we are here now. Let's say we are here. X meters away. So let's say this is X. So there's a slab below me with thickness H, and there's a slab above me with thickness H minus X. So the electric field at point B, the electric field at point B is going to be the field from the slab above, so slab below, taking upwards is positive. Field from the slab below, so it's going to be rho X over 2 epsilon naught minus the field from the slab above, because it's pushing the other way. It's pushing me down, minus rho H minus X over 2 epsilon naught. So, and that makes it so rho over 2 epsilon naught, and it's going to be 2x minus h. So inside the slab, if we're inside the slab, the electric field is going to be this. And we can perform a sanity check here. Right in the middle of the slab, what do you expect the electric field to be? What's the electric field if the slab is positively charged? So right in the middle, what's the field going to be? Zero. Yes, because you have exactly the same amount of charge above and exactly the same amount of charge below. And because it's uniformly charged, you have zero charge in the middle. Therefore, if X is, so sanity check. If X is H over 2, if we are right in the middle, well, H over 2 we substitute and we have 0. The electric field is 0. Okay. And yeah, that's pretty much it. So, oh, I said Z. Okay, I should have used Z. Anyways, I can plot the graph now. And this is the electric field. And this is the z-axis. So at the bottom, it's going to be negative because it's down, and the value is going to be minus rho h over 2 epsilon naught. So when z is equal to h, it's going to be positive, the same value but positive. So it's going to be rho h over 2 epsilon naught. And then we're just going to go like this. So when z is h over 2, it's going to be 0. And then like this, and on the left like this. So below the plate is going to be negative and constant. Inside the plate, it will change, and then it will be constant again. So this is a very common graph, as you can see here. This is a graph of E for the charged sphere. So for a charged sphere, the electric field, so we are measuring from the middle. We're measuring from the middle, and This is the x-axis, x-axis. And if we were to draw a graph of the electric field, in one of the questions, you need to prove that the electric field inside the sphere is 0, doesn't change. And then outside the sphere, it behaves just like a that's just like it's an inverse square law, so it's proportional to 1 over r squared. So x, and this is the radius of the sphere, and this is electric field. If you look at the the electric potential inside a sphere, and this is a very important result as well. There's one thing you need to understand, that that's the electric potential V with respect to x. You need to understand that the electric field is the derivative of the potential with respect to the distance from the charge, or the distance overall. The electric field in a given direction is the derivative of the potential with respect in that direction. So if the electric field is 0, that means the derivative is 0. And if the derivative is 0, that means that the electric potential, which behaves like this, it's proportional to 1 over r, and you can, I'll leave this as an exercise to prove it, because it does not change. Inside the sphere, the potential does not change. And it means that if at the surface of the sphere, the potential is this much, it will be the same throughout the sphere. So 2 important results. Inside a charged sphere, a charged, I'll actually say shell, inside a charged shell, the electric field is always 0. And the potential is constant. It does not change. Because if the potential did change, you would have a flow of current. Because current always flows from large potential to low potential. If that makes sense. I'm rushing it a bit because I do have to go in a few minutes. So let's look at this question. 2 charged concentric spheres of radius r and r carry positive charges of q and q, respectively. The switch is closed, the charge redistributes. Find the new charge on each sphere. And we know that the electric potential obeys the principle of superposition as well. So the potential on this surface, let's call it V2, is equal to the potential of the outside sphere, and the potential of a sphere is Q over 4 pi epsilon naught r, which is the radius of the big sphere, plus the potential of the inner sphere. But it's also at the same distance from the center of that sphere. So it's going to be Q small over 4 pi epsilon naught r small. Oh, sorry, not r small, r large. Epsilon naught r small. Right. and V1 is the potential on the surface of this sphere. Don't worry if you don't understand it fully. It takes a while. It takes a while to process. The potential on the inside sphere is because the potential of the outside sphere is constant inside the sphere. So it's equal to Q over 4 pi epsilon naught R large plus Q small. So because inside the sphere, the potential is always the same, it's constant. But outside the sphere, it obeys this law. Yeah. So the potential of the outside sphere is the same inside the sphere. Sorry, so 4 pi epsilon naught R small. Now, can somebody compare V1 and V2? V1 and V2, you need to compare them. Mathematically, we're not, this is not a physics question. V2 is bigger than V1. Why, Josh? Or is that a 50-50 chance? V2 is less than, of course, because the only difference between them is that small r here and the big R here. And V1 has a small r, therefore V1 is greater than V2 as long as Q is not 0. Well, yeah, as long as Q is not 0. And that implies that as long as there is charge on the inside sphere, charge always flows from high potential to low potential. Current always flows from current flows from high potential to low potential. Therefore, until the inside sphere is not charged, the charge would be 0. And on the outside sphere, the charge is going to be Q plus Q. So it's a simple solution, simple answer, not really a simple solution, but this is like more like a qualitative thing. This is what you would typically get on an interview question. You potentially could. I mean, it's a tough question. Probably this is kind of question you would be asked if you were to go for a PhD in physics. They like this sort of questions. But anyway, it's an elegant problem with an elegant solution. Lots of stuff to think about. I think it's rather philosophical, like realizing that things always go from high to low. Heat flows from higher temperature to lower temperature, and current flows from high potential to low potential. And until there is charge on the inside sphere, there will be higher potential on the inside sphere than on the outside. All right. I do have to run. If you have any further questions, do type in the Telegram group. Otherwise, no, there's going to be one more next week. This would be the last one. Right, we finish when school finishes, basically. Right, there's one more now. See you everyone. It was a great pleasure seeing you. Right.